problems?
Mexico would like to challenge Team Hong Kong to report problem number 10.
Okay.
You accept?
We accept the challenge.
Okay, problem number 10 accepted, and the reporter have 5 minutes to prepare, but whenever you're ready, you're free to start, okay?
Switch. Okay.
Oh, I'm sorry. Hey, wait, testing. Hey. Okay, I'm ready. So, mhm. Good afternoon, good morning, everyone. Today I'll be presenting problem number 10, Rayleigh-Bénard convection. So here's the problem statement and investigative parameters. So first onto our qualitative explanation. The Rayleigh-Bénard system operates on a simple principle when fluid is heated from below. The bottom of a container becomes warmer than the top, creating a temperature gradient. Because warmer fluid is less dense, it rises, while cooler and denser fluid sinks. As the warmer fluid rises, it creates a continuous flow. Warm fluid ascends, cools at the top, cools at the top and sinks back down and is reheated again. This process forms convection. As the warm fluid from one cell rises, it pushes against the fluid in a neighboring cell, causing the denser fluid from the neighboring cell to sink into the space left behind. We now define driving mechanism and dissipation mechanism. Driving mechanism is actually due to the density difference driven buoyancy, and gravity and viscous drag oppose the motion, thus is defined as dissipation mechanism. We now have three phases. The first phase is when the dissipation mechanism dominates. The system remains in uniform conduction, and when the dissipation mechanism and the driving mechanism is equal, it is the critical case that we aim to investigate. And for the third type, the driving mechanism dominates and convection is happening in the system. We also conducted some preliminary experiments to identify existing issues and test out relevant parameters. Our approach involves recording fluid motion and measuring the temperature difference for each trial. We can then analyze the relationship between parameters and fluid behavior. So here are some necessary assumptions that we made, and we'll explain them in detail when they appear. So we first consider a fluid particle with volume V, density rho, and velocity u. We also have for incompressible flows, we have an equation for continuity for incompressible fluids. So this is the Navier-Stokes equation. It states that the fluid's density times its acceleration equals to the total external forces acting on it. And when fluid moves due to small disturbance, we can simplify the equation by removing the term that involves velocity since it is small. So to describe how density changes due to temperature, we use the thermal expansion formula. We apply similar steps to the heat equation, which explains how heat spreads through a material over time. Additionally, we also impose the Boussinesq approximation, which allows us to ignore most changes in fluid properties except for density changes due to temperature difference in the vertical direction. We now model the perturbation, and with the help of literature, we now arrive with the dimensionless form of the three equations. We introduce the non-dimensionalized parameter Rayleigh number to make the temperature variable theta here dimensionless. The Rayleigh number actually measures the strength of convection in fluid, indicating how heat moves due to temperature difference. Another parameter is the Prandtl number, which compares how quickly momentum spreads in fluid to how quickly heat spreads. It depends only on the type of the fluid. And since the driving mechanism is buoyancy driven, we now express our results in the term of W, Prandtl, and Ra only. Now we will talk about the boundary conditions. At the top of the bottom of the fluid, where air meets oil, we consider it as a free boundary. At this point, there's no vertical velocity, the tangential stress disappears, and we reach a thermal equilibrium. The mathematical expression is as such. And also, at the oil and acrylic boundary, we consider this as a rigid boundary. We impose no slip boundary condition here. And going back to the expression for W, we see that this takes a form of a linear PDE. Therefore, we know that any linear combination of the solution is also a solution, and they can be expressed as products of spatial and temporal components. We simplify the problem by using the general normal mode solution for the linear system. Due to linearity, the amplitude can be scaled arbitrarily, so it does not affect the eigenvalue, so it's left undetermined. So these are the steps to solve the eigenvalue problem. I wouldn't go into depth of how we solve that, but we can discuss it in our discussion later. So with the simplified form of the PDE, we can rearrange the Helmholtz equation, which is the eigenvalue problem, to obtain the expression for R, which is the Rayleigh number, where D is defined as the operator of D over dz. As mentioned, we expect the fluid to exhibit a sinusoidal behavior, so we can let Wz to take the form of a sine function. The expression for R can now be derived, with n being the mode number of the solution. And since lower modes tend to be more stable, it is already unlikely for the system to choose a higher mode, as the fundamental mode, which is n equals 1, is already showing instability. Therefore, we will assume that n equals 1 for further calculations. So now this is the plot of the Rayleigh number against A. We observe that a minimum value for R exists. So to find this minimum, we simply set the derivative to equal 0, and we yield a critical Rayleigh number for rigid free boundary case of 1100.7. And the corresponding wave number A here is 216. We also present our theoretical simulation here. The Rayleigh number is 1,900 and 400 respectively. So we see that when the Rayleigh number is larger than the critical value, the fluid is unstable and convection rolls are formed. And for Rayleigh number that is less than the critical value, the fluid is stable and uniform conduction occurs. So onto our experiment. This is our experimental setup. Video is recorded vertically upwards from the liquid surface. A spirit level is mounted to ensure proper alignment, and the oil is contained in an acrylic container heated from below using a heat plate. We also added a copper plate coated with oil to ensure even heating. We now test out 4 different factors of different viscosity, different oil heights, and different heat plate temperatures. To maintain consistent oil heights across the trials, we marked increments of about 5 millimeters. We used a digital caliper to measure the dimensions and a thermocouple thermometer to check the temperatures of both the bottom and the top surfaces. As we mentioned before, several parameters of oil, including thermal expansion coefficient and thermal diffusivity, cannot be easily measured with school laboratory settings. Therefore, we would use values quoted from literature. The measurements and details of the experiments are as shown. And this is, we test out the viscosity against temperature, and we see that it is affected. So from the simulation, we observe that convection rolls in the 50 centi-Stokes case, but not in the 500 centi-Stokes case. This suggests that the Rayleigh number did not exceed the critical value when viscosity is 500 centi-Stokes, indicating that the fluid remains stable and only uniform conduction occurs. Well, we also see that in our experimental results, a higher viscosity requires a higher time to reach stability, and no patterns is observed in the 500 centi-Stokes case there. A qualitative explanation is that less viscous liquid, the fluid moves faster, allowing the buoyancy-driven convection to overcome damping forces, which we mentioned as viscous drag and heat diffusion. This creates instability and strong convection. Well, in contrast, for higher viscosity, heat diffusion dominates because the fluid moves slower, resulting in a more stable system where convection cells do not form. Now looking at the cells, we can qualitatively observe that as viscosity increases, the size of the cells increase. This can be explained by the relationship of the Rayleigh number and the wave number A. So it is expected that the cell size decreases as Rayleigh number is increased. Now we vary the oil height. As oil height increases, the temperature difference in D also increase accordingly, and the Rayleigh number will also increase. This trend is agreed by our experimental results. It is observed that the thinner the liquid, the faster it is for cells to form. As heat from the bottom can easily affect the entire fluid, velocity increases and driving mechanism dominates. Whereas for a thicker oil layer, velocity decreases and dissipating mechanism dominates, making it to take longer for the cells to form. As we previously predicted, Rayleigh number increases as oil height increases, thus lambda decrease. Cell size is experimentally proven to decrease generally, which agrees with our predictions. The lack of energy makes it unlikely for large cells to form, as fluid tends to form more compact cells to ensure stable energy distribution. Now we vary the temperature of the heat plate from below. As temperature is increased, only delta T increases accordingly, so intuitively the Rayleigh number will also increase. The trend is again agreed by our experimental results. The reason for a faster cell formation is similar to the previous. As the temperature gradient is greater, the velocity of fluid increases, driving mechanism dominates, and circulation of the fluid is faster. Though experimentally, the difference in temperature gradient may be too small for us to notice a significant difference in behavior for the 60-degree case and the 70-degree case. Following the previous discussion, the Rayleigh number increases, so the wave number increases. Therefore, the cell size decreases. Again, the difference is it's too small for us to see a significant difference between the two cases there. We will now qualitatively discuss the possible shapes of convection cells. One way to create different shapes is by using different containers. We tested out two types, a rectangular container and a cylindrical one. And we record the resulting cell shapes. According to the Helmholtz equation, the cell patterns can be seen as possible solutions that cover an infinite plane, suggesting they should be regular and symmetrical. However, in reality, we must consider the boundary effects, which influence fluid movement in different directions. This interaction leads to the formation of convection cells with different shapes. So this is a side view. We can see that lateral boundaries impose an effect on the orientation of the parallel rolls made inside a fluid. The rolls would be parallel to the shortest side of the container. This is the top view for our box containers. With the straight boundaries, the convection rolls again align with the edges, resulting in a rectangular shape of different ratios. For example, square cells are the result of two rolls of same wavelength going perpendicular to each other. And in cylindrical containers, we observe that irregular polygons and a little bit of genuine hexagon cells are formed. This is the equation for the velocity of the cell with hexagonal shape, though we notice it's difficult to match our experiments with this. So to conclude, we theoretically quantified convection motion using the Rayleigh number, identified critical conditions for convection to occur, made general predictions, explained how different parameters affect convection. We also did a numerical simulation of convection using MATLAB. Experimentally, we tested out different variables, reproduced different shape of the cells, qualitatively analyzed and explained the fluid motion and cell patterns. We also observed trends that matched with our theoretical predictions generally. And that's all for me, and thank you for your attention.
Okay. Yeah. Opponent, please question the reporter.
Okay. First, what would you think is the main cause to form the cells?
I'm sorry.
The main cause to the form of the cells.
Main cause?
What causes?
The Rayleigh number, which we can see that is actually...
Only the Rayleigh number is the main cause?
No, actually we have different parameters, but all of these parameters are concluded into one single
That is the Rayleigh
characterization.
Number.
Yes.
Okay, thank you. Did you try another type of powder or only mica powder?
No, we didn't use mica powder, as we said, because why? We tried mica powder in our experimental previously, but we ended up using graphite powder. This is because
Using what type of powder, sorry?
Graphite powder.
Okay.
Because mica powder actually sinks to the bottom, and we think that is uneven.
Okay, thank you. You mentioned that the powder sediments. This is because you made a solution or a suspension?
A suspension. A suspension of powder is
But
the
a suspension, the powder sediments or not?
This is why I chose
Yes
to
or
not
no?
use in
Okay,
graphite
thank you.
powder case.
Another topic, did you try another type of oil?
Yes, we did. We varied different types of silicone oils with different viscosity
Only
and
types of
diffusivity.
silicone oil?
Yes, silicone
Okay.
oil itself has
Thank you.
different oil
Also,
properties.
in what moment did you take the photo of the cells?
We waited for the cell to stabilize to take
And
the
what
photos.
would you call stabilize?
What?
What would you call stabilize?
When the cell patterns don't change.
And what is the amount of time when it doesn't change?
What? It varies for different cases, but approximately
an
generally
average?
4 minutes or so.
4 minutes?
Yes.
Okay. Also, does the cell size increase only due to the Rayleigh number?
It is also related to the aspect ratio of our container, but yeah, Rayleigh number also causes the shell shape to differ.
Did you consider the Grashof number?
Grashof number? No,
Yes.
we did not.
But
This is
Grashof
the
number
linear
isn't
theory.
included in Rayleigh number?
What?
Does the Grashof number isn't included in the Rayleigh number?
It is an extension
Okay,
of
thank
our...
Okay. Yeah, this prepares time for the opponent.
It's fine. 换了一套。
Let's start.
Opponent from problem number 10, that is Rayleigh-Bénard Convection, and I'm from Team Mexico. First, we have the problem statement just to have it in mind. However, we highlight some important points of the powder in oil, that is like the principal parameters. Then we have the analysis of the reporter. She mentioned some important points in the theoretical approach that are the most appropriate or accurately for this problem, that is the Rayleigh number, the convection process that she represented in a theory and mathematical model, as well as the Bénard cells, how they form. She changed the types of viscosity with the different types of oil. However, she only tried with the silicon oil, the heat, as well as the formula. And there she has the thermal diffusivity, the Navier-Stokes, and the boundary conditions, which are very accurate for the problem. Then we have her experimental setup. She had the measure and changed the amount of oil, which is pretty good, just to have the measures of the experiment. Then she about the powder also, and varying the viscosity, which is very appropriate, and a transparent container, which is perfect to see how the cells are formed, and the height of the oil to calculate it, and the thermometer that she used. Then we have her results and conclusions. He compared with the theory, which is very crude in her graphics, also the different types of shape, and the 4 different variables that she used: the viscosity, temperature, the gradient, the amount of oil, and the geometry of the container. Then we have her qualitative analysis, which was great, and she observed trends and matched theoretical predictions with the theory and experimentation. However, we have some weaknesses and areas of opportunity that will be related for our topics of discussion. First, we have the mica powder. I mean, I know that you use the powder that you mentioned. However, the problem establishes mica powder, and we can talk about the characteristics of each powder in the discussion. And you could try also how different types of oil, not only change viscosity. We know that different types of oil that you use, that was silicone, have different viscosity. However, other types of oil of materials, I mean, not only that comes from silicone, have also different viscosity. So we can also talk about that in the discussion. To how it affects the results. Also, the measure of temperature, do you use a thermometer? However, I want to talk about some important topics about talking about the thermometer. I think that some graphs miss the margin of error, but it's okay, you can give it to me in a moment. And the suspension, you mentioned that the powder tend to set on the bottom of the container. However, we talk about the difference between suspension and solution. And that will be all for my part. I don't know if you want to start the discussion. Yes.
So regarding your question about the powder and the oil that I used, I'm sorry I really didn't include this photo in this slide, but we actually did a preliminary experiment using vegetable oil and the mica powder, which is stated in the problem statement. But the reason why I changed to graphite powder and a silicone oil, this is actually due to what I said there. Mica powder, we see that it actually sediments to the bottom. And because that we know that graphite powder has a lower bulk density than mica powder, so it actually doesn't sediment as much, and it actually suspend more evenly in the liquid. So that's why we changed to graphite powder for better visualization.
Okay, you mentioned that it's suspend. This suspend is because how do you mix the powder with the oil?
We just mix
With
it
a-
with 10 because it's
Yes,
I
I know.
know what you're erasing, because when the powder is like uneven in the fluid, it will actually the
Huh.
like affect the result if you're questioning about that. But also you know that it's very hard to actually ensure that it's even,
Yes.
right?
Uh,
Like if the only way you can do is like to put the powder bit by bit, but that's why we chose graphite to avoid this
Okay,
experimental
you mentioned that you mix it. In the moment that you mix it, in that exact moment you put it in the heat to be in contact.
Yeah, we ensure that it's
And why did you
even
mention that it
separation.
tends to set on the bottom?
I'm sorry, can you repeat that?
You mentioned first that you mix the powder with the oil, and
Mhm.
then you put it in the
Container.
container.
Yeah.
Well, in the container and be in contact with heat.
Mhm.
However, you mentioned that it tends to set onto the bottom. Why does this happen if you already mix it?
No, I was not stating that it will sediment to the
What?
bottom. To avoid, instead, to avoid that it will sediment to the bottom, we changed the powder. That is stated in the problem statement, because we observed that it will sediment to the bottom, and to avoid this, we changed the powder so that it does not sediment to the bottom.
And that only happens in that experiment or in all your experiments?
In the preliminary experiments, and
That was
that's why
the
we
one with
ditched. Yeah, this is why
vegetable
we
oil.
ditched the old experimental.
And that's why you changed to silicone oil.
Yes,
And
yes.
have you tried silicone oil with the mica powder?
Yes, we also did, and that's why we see that it doesn't like the powder and the oil doesn't mix as well as the case with graphite powder.
And what is this main cause?
Because the bulk density of the mica powder is higher than the graphite powder.
Is it because it's an oil and not water?
It's about the powder, not about the oil.
So it's not about talking about the density and
No,
the
not the density
viscosity
of
that
the
you
oil.
mentioned?
Not the density of the oil. It's the powder.
It's not due to the oil.
No, 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 no.
Okay.
So that's why we also only change the powder, not the fluid. Yeah.
Okay. Also, can you put the picture of the thermometer that you use?
Okay, sure. Here.
Which one is? Sorry.
Okay, sorry, let me point it to you. So these are two probes.
Are the one in blue?
Yeah, the two thing in blue, and this is the one showing the temperature,
Ah,
or
okay.
like that is the one showing the temperature.
And did you measure both temperatures, the one on the top and the one in the bottom?
Yes, simultaneously.
That for the Rayleigh number.
Yeah.
Okay. And that apparatus have a margin of error?
What?
I mean, you measure it with the hand. You were holding the strings, for saying like in this way.
Yeah.
It would be better if you had like a holder to hold these strings.
Oh, that's because like we assume
Because
that
it
the
is moving-
temperature gradient is actually uniform across the horizontal extent.
Yes, as
we
you show
also
in your
verified
pictures.
that experimentally, so that's why the horizontal position of the injection of thermometer is not a significant issue in our experiment.
No, but I was talking about the human intervention, because I think that you put your hand, and but isn't your hand moving, and it doesn't affect how you measure the temperature?
Yeah, that's why I was saying that I'm sorry. Yeah. So this is why I'm saying that across this extent, the temperature variation is very less, and that we do not consider the horizontal position of the injection of thermocouple thermometer to affect our results as much.
Well, what I was referring is that you have your container. Here is the liquid, and here you have the two strings, one on the top,
Yes.
one on the bottom. My question was about your hand intervention. Isn't your hand moving, and this isn't like, it's not constant in the same place, so it will affect the
You're
temperature.
talking about the vertical displacement.
About the two, about these two strings.
Yeah, so because like our temperature gradient is actually like is not that big for a very thin layer.
But however,
we try to stabilize
You
it.
mentioned that it was the different temperature between the 10 Celsius degrees, right?
15,
10.
10, yeah.
And also, if you are having your hand here, I think that you are also pretty close to the experiment. Isn't your respiration also doesn't affect the experiment?
Oh, so
About-
you're talking about the injection of the the thermometer to actually affect the cell shape form.
The injection of what, sorry?
The thermometer, sorry.
Yes.
Oh, this is because the probe we use, sorry, can I borrow your
Sure.
pen? Is actually very small, like it's only like one string and then one small probe here. It's not the usual thermometer we use with
Yes,
like
I
a-
know.
So this small point of contact would not affect our cell formation, and this we take the temperature data after we
So-
take the cell pattern.
Use thermometers while in the whole experiment and only when the temperatures you need.
No, so like here we have an oil, right?
Yes.
And then it's stable. We take the photo there, and then after we take the photo, we
You take it away?
Yes. No.
And
no.
that doesn't affect the cell formation?
No, it does not, because the size of this thermometer is very small, and it is injected in the latest step or stage in our experiment. That's why we believe that it will not affect our experimental results.
Okay, and also did you measure the length of the cells?
The length of the cells.
Yes.
Yeah, but this is the reason why we only choose to do it qualitatively, because we see that the cell formed is actually very irregular, and according to the theory, the only three parameters that can be verified experimentally is the critical temperature difference and the critical Rayleigh number, and also the
But however, you mentioned Rayleigh number and Grashof number is included in Rayleigh number and you didn't calculate it.
Are you talking about the Grashof number or the cell size?
Yes, that is included in the experiment.
I'm really sorry about that.
The Grashof number that is included in the experiment.
Oh, we didn't calculate the Grashof number, and can you explain like why do you think that this affects our theoretical prediction?
Because the
of
Grashof
our-
number, it also plays an important role because Rayleigh number includes density, difference in temperature, and some constants like beta. However, the Grashof number also includes other constant parameters and also other parameters that can be calculated in the experimentation, and these complement each other. So that's why I think that it's important to have it in your
Okay,
theoretical model.
so I would argue that because we consider the Rayleigh number and the Prandtl number, one is defining the motion of the fluid and one is defining the properties of the fluid. And we believe that this is sufficient to give a qualitative explanation and also a quantitative explanation on the critical Rayleigh number that determines if the possibility of convection cells forming or not.
Okay, talking about the convention, you prove the length of the height of the oil.
Yes.
How do you measure that height?
So let me show you this slide.
You measure it inside or from
here.
the outside
Inside.
with the vernier?
Yeah.
So you put the vernier inside the
Yeah, because the vernier has a you can pull
yes,
it up
but
and
that doesn't also affect the cells formation, or you measure it before
No. Okay,
it
so
starts.
here I wrote that we wrote marks of about 5 mm onto the container. This is done before all the experiment.
And talking about that, what is the amount of oil in that picture?
The amount of oil?
Yes.
I didn't have the exact value of the volume, but I have the width and the height and also the base area. I didn't calculate the volume, but yeah, it can be obtained.
Okay, you also mentioned that you tried different types of containers. Here's an example of a rectangular square.
Yes.
Did you try with a circular one?
Yes, we did. Let me show you the photo.
It was a Petri or a beaker?
What?
It was a Petri dish.
Pantry dish.
Did you
Petri
try it
dish.
with a beaker?
Yes, we did, but because we think that the Petri dish provides a bigger area, and the effect of the lateral boundary is less compared to the beaker, where the boundary is a little bit the area is smaller. The lateral boundary is actually affected more. Let me show you this.
So do you think that it's better to do it with a beaker or with a Petri dish?
Okay, so this. Let me. Okay, so that's the video we took with the infrared camera. Maybe you can see it here. Yeah, and then this is the dish that we used. You can see that the cells forming at the edges are actually irregular.
These two are the same?
Yeah, these two are the same.
And why in the one with colors you have more circles in the middle
because-
and in the other you only
Because
have
this is
three?
not stabilized yet. Give
But
it
you
some time.
Well,
Yeah,
I have seen the
this
video
fine.
and they are the same. However, you also mentioned the height. Does the height doesn't change it when it receives the heat application?
The height? You mean the oil height?
Yes.
Yes,
I mean,
the oil height is very.
As you know, oil loses density when it is heated. Does this affect the experiment?
You mean the density variation with height? Of
Eh,
course, it affects the experiment. It is the major driving mechanism that makes this phenomenon to occur.
And the main cause is the Rayleigh number or the heat application?
The heat application changes the Rayleigh number so that the convection can occur.
But
That's
at the
my take
beginning,
on that.
you mentioned that the main cause was the Rayleigh number.
No, Rayleigh number is to quantify what happens, but the qualitative thing that causes this thing is when you heat the thing
Okay.
up from the bottom.
Another topic is that you mentioned that it takes an average of 4 minutes to the cells to form. This
yes.
happens in what container? In the square one?
It's a very general time, as you can see. 4 minutes is actually a security factor so that I ensure that it's actually stable. But the time for stability is actually less than 4 minutes, as you can see.
Okay, well, that will be all. Thank you.
Thank
Okay.
you.
The opponent give a summary talk.
Okay, for the conclusion, I think okay, for a conclusion, I will say that the reporter did a great job in the theoretical model. However, I think that she missed some points, such as the Grasham number, and he could also compare it. She mentioned that the Rayleigh one is the main one for the experiment, and that is good. However, she could background it with the Grasham number also. She had the measures of the different types of oil viscosity and the parameters that she used. However, she could put more picture or compare it better between the video and the photo, because as we see in her video, it wasn't the same as in the picture. So that's why that she could take like better ones. I know that it was unstable and the one that in the picture was stable, but I think that she could put the ones to be the same to have a better comparison. Also, the parameter that she used between the experimental setup and the one before, it is good. However, she could put like, why is it better in the experimental setup and why isn't better the one before, just to have or to prove the parameters that she used. Thank you.
I would like to ask the reporter, what was the lowest Rayleigh number that you saw in your experiments?
444.
Okay. And does the Rayleigh number directly changes the size of the cells?
Yes, the size of the cells is affected by the Rayleigh number.
Yeah,
And
but
also the
it's
aspect
the
ratio.
only
it's not
parameter
the
that does
only
it change?
What?
Okay,
I'm
never
sorry.
mind.
Please.
I would like to ask the opponent if he thinks that the temperature difference change in time,
Yes.
and how does it affect the experiments?
It affects due to the height of the oil. If you have a bigger height, it is more time, so it takes more time to the cells to form. If you have a lower height, it's the opposite.
Yeah, okay. And I would like to ask the reporter again,
Yes.
how does the adding the graphite powder affect the parameters of the oil that you took from the literature?
We actually checked the viscosity of the oil with the graphite powder, and we didn't see a significant difference because we added only a little
Yeah,
amount.
and
like
what
a
about,
teaspoon or
for
so.
example, the thermal diffusivity?
That's very hard to experimentally verify, but we believe that it does not have an effect, and it's only for visualization.
Okay,
effects.
and
Yeah.
I would like to ask you again, what was making the color differences on your experiment? Because we could see the cells,
Oh,
and I would like to ask, why are there the color differences?
That is a very, very good question. I have been thinking about that. Okay, so at the cell boundaries, we actually see that it's a lower temperature, and the flow of the fluid actually makes, and we believe that makes this difference, because the flow at the boundaries are flowing down, so the concentration of the powder would actually be higher in this
So you think
band.
it's about the concentration of the graphite?
Yes, we kind of
Yeah.
believe so, but
Yeah.
I'm not sure
Yeah,
about
okay.
this.
Could it be, for example, affected by some suspension or some
Yeah,
oil
we
that the graphite that's suspended on the ground, and there was difference
No, we
in
don't
concentration?
believe that is because of the sedimentation of powder on
Yeah.
the bottom, but we believe that because it's the concentration of the flow, and that such that the more powder sediments
Okay.
at the lower the boundary of lower temperature.
Yeah, thank you.
Yes.
And what about opponent? Do you think that this is the main cause of the color difference?
The what?
Color difference, because we could see the patterns, we could see the cells, so why could we see them?
Can you reformulate, please?
Okay, never mind. You asked a lot of questions about indicator. Is the indicator really that important for the convection, or would the convection work without the indicator?
Which indicator you mean? The one that makes the mix?
Yeah.
I agree with the reporter that it is a good way to make the mix. However, I was asking about what it is
Quickly, please.
tends to sit to the bottom because it's a solution and not a suspension.
And would the convection work without the indicator?
No, it didn't because the powder tends
Okay,
to stick
thank
to the
you.
bottom.
Thank you.
So I would like to start. I would like to start the review of the task number 10, Rayleigh-Bénard convection. So I would like to start by the analysis of the reporters. So we really liked how the reporter did the qualitative explanation and also explanation of the phenomenon and how what is the difference between the conductive and convecting thermogradient in the convection. She described the parameterization of those equations and derived the Rayleigh and Prandtl number, which we find really nice for the explanation. She mentioned the boundary conditions that they used and also that they used in the simulations. They had a very nice qualitative agreement with theory, and she described how the shape of cells depends on the container that they used. One thing that we think that kind of liked was that the simulations a lot of times had higher Rayleigh numbers than they had in their experiments, and also that they, which we understand that it's very hard to measure the diffusivity or thermodiffusivity of the oil, but we think that's one thing that would be very nice to do. Now I would like to move on to the opponent. We liked kind of the opponent's question about the experiment and how the hand could, for example, somehow change the experiment and all the error measurements that they could use. We like that the opponent showed some knowledge about the phenomenon and some basic understanding of the problem. But we think that he was too much fixed on the indicator problem, which we don't find that relevant, and we agree with the reporter about that. And we also think that he was too much fixated on the experiments itself and how they were conducted. He also didn't talk about the simulation, and he didn't talk much about the theory, only about some number which we don't find that important. I'm sorry. In the discussion, they were talking about the different indicators that was used. They also talked about the thermal measurements, which we found kind of irrelevant for this specific case. They also talked about how they measured each of the parameters and how did they change the height. And also when was the time when the reporter defined the stable convection. So now some specific points from the presentation. They discussed if using of the indicator somehow is important for this phenomenon. Reporters said that they used graphite for better properties, which we completely agree with, and we can say that for us it's completely fine. But the opponent still thinks it's really important to use mica powder, which we kind of don't understand why. Also, they talked about the human effect on the experiment. Reporter was saying that their thermocouples were really small and that it didn't affect the experiments. But the opponent said that the hands and the heat from the body was important for the measuring of temperature, which I think is it's not true for this case. So we agree with the reporter. And also, the reporter said that the size of the cells is purely affected by the Rayleigh number, but we agree with the opponent that it also depends on the height. So in the conclusion, I think that this is all for me, and I thank you for your attention.
The reporter and opponent for the discussion, and at this very last stage, I would like to clarify on some things that that was raised by the opponent and the reviewer. So first, theoretically, the Grashof number, it actually, we agree that the opponent that it includes some of our experimental parameters, but what we would argue is that it does not indicate anything significant about the convection motion that we aim to investigate, and the Rayleigh number itself is sufficient to explain why convection and when convection will occur. And so on to our experimental point. Regarding the thermometer injection, we did it in the steady state, so we agreed with the reviewer that it does not have any significant effect on our results. And also the mica powder is merely a visualization tool for us to capture the phenomenon, and we believe that convection will still occur regardless of this presence of this indicator, which kind of contradicts with the opponent. And regarding our simulation, we would like to say that we actually used the values of our experimental here. That was what I say from the lowest Rayleigh number that we have is like 400 and something. And we actually used this value to conduct our numerical simulation. And regarding the why the patterns are seen, we believe that this is actually due to concentration difference due to the fluid motion. And lastly, I still have some time, and okay, this is, this is what we get from our experimental setup, and this is the justification for why that we see the cells. This is the I don't know how to say that, but yeah, we can see that the temperature is lower at the cell boundaries, and this is why we believe that we can see the cells, and convection occurs is also seen there in the, it's not very clear though. That's all from me, thank you.
Okay, thank you very much. Okay, this is the time from the jurors, and please give a concise and short answers for each question. Okay, any?
Thank you for a nice presentation. I have a question about your simulations.
Yes.
If you go to, well, say slide 30, I think.
Here?
Yeah, this one.
Okay.
So in how many dimensions are you solving the equations?
2D. This is an exact plane because we were, the computational power was not enough for us to solve a 3D simulation.
Okay. So in the lower panel,
yes.
You said that you would get a certain wavelength, this critical wavelength,
yes.
AC. So, but this is obviously not periodic, the lower panel.
Like the simulation may not have a predictive power on the critical wavelength. I'm not sure if you're stating about if the simulation does not have a predictive power on the wavelength.
No, I'm just asking, you know, why is, I mean, there is clearly different distances between the peak, right? But the theory you presented said, okay, we have the sinusoidal stability with some wave vector and so on.
Yes.
But this one is obviously not purely periodic.
We believe that this is due to the cell size. So, yeah.
I'm not not sure, did I understand correctly? During your presentation, you said that the cells would, do you think that the cells, convection cells would occur without the powder?
Yeah, yes, we believe that the fluid will still have convection motion without any indication of powder.
Okay, and for the opponent, what parameters in Gratian number did the report miss that you think are relevant?
Well, Rayleigh number equals the Gratian number times another number, so it's a fundamental part included in the Rayleigh number, so that's why they are missed. I mean, I cannot give it to you because I don't remember, sorry, but the Rayleigh number equals Gratian number times another number, so she's missing like one part of the number. For the Rayleigh number?
Okay, I have the question to the reporter.
Yes.
You compare the trends on the effect. For example, on the slide 29, 28, if we can, yes, for example here,
Yes.
You can see that the effect should be proportional to the temperature difference on the third power of the D. Did you try to make more qualitative comparison if the effect depends with the power law of the D or something like this?
Okay, so since the analytical solution is quite hard to obtain due to the NS equation, so we only have a numerical solution to this. So we couldn't actually provide you an analytical relationship between the parameters, but we could definitely plot out the Rayleigh number curve and regarding the different parameters. But since, like for example, this case, the delta T is actually not independent itself. It's kind of related to the oil height, so it is hard for us to plot out one single graph with the Rayleigh number as the y-axis and the parameter as the x-axis. Yes.
I have a question to the reviewer. Also, you mentioned that the height would change the cell size. Can you explain qualitatively how? Can you explain qualitatively how the height affects the cell size?
That's something that is important for the convection, that the Rayleigh number does not influence the size of the cells, but it defines how the size of the cells divided by the height of the oil changes. That's something that you could see. That's, for example, the Rayleigh number defines the wave number that they had. And that's something that's in the dimensionless form. It's the same thing, that the Rayleigh number correctly describes how the x or the size divided by h is. Yeah, because when you have the same Rayleigh number, but you have bigger height, then the cells won't be, because of the instability that is here, the cells wouldn't be that small. They would, that's something that the reporter said, that the cells would collide to each other and they will form bigger cells. So for the same Rayleigh number, it will be different sizes.
Thank you. Do you want? Thank you.
I think all the jurors are ready, so we'll raise the score. Okay, first for the reporter. Let's have a score. 57774. Okay. Then for the opponent, 63444. Okay. And for the reviewer, 68778. Okay, again, we have some variations, so let's hear it. Okay, let's see. Please, jurors, this time make a concise comments, Please do not take too much time on one jurors. Okay, let's see. For the reporter, we have a high end at the 2.7. So one of you guys have some. Oh, these two has some comments.
Yeah, so I'll state my partial grades. I have a 3.75 for the report and a 2 for the discussion. Yeah, so I mean, in the columns, right, like I thought your phenomenon explanation was good. Your theory and model were good, but you got the most point for the multitude of parameters examined. And then I also thought that your science communication was very good. And yeah, this is where I gave you more points than in other reports.
And I'm a harsh judge during this session. It was completely different from the previous one, but I gave you 1.5 for the report and 1 for the discussion. And what I suppose maybe it's because at the beginning you were nervous. You didn't explain at the first part a phenomenon very well, and I missed what happens on the surface with the surface tension and how it affects the motion and the surface tension difference with the temperature, and this affects how the cells form. So I missed that part, and the rest I actually agree with her, but my judging scores are lower by so I'm sorry about that.
Okay, that's okay. Okay, for the opponent, I have a high 6, which I didn't think is high, but somehow relatively was the highest. I gave it 6 because even though some of the minor questions asked, many times, but there were some few questions, the important questions asked, it should be asked. So I kind of evaluate as a, like a fair opponent argument. So in my scale, that's a little bit of the above the average, just a little bit. That's a 6, so I come up with a 6. And there was a 3 from Andrea.
Yeah, it was somewhere between a 3 and a 4. The reason for the low score was that you spent a lot of time asking about things that were not really relevant to the convection phenomena in and of itself, especially the discussion about the powder, measuring the temperature and so on. I thought you could have spent your time much more efficiently discussing sort of the actual physics and especially some of the points that the reviewer brought up.
Thank you. And for the reviewer, I have now low 6, but it's the same reasoning actually. You did what you should do in kind of an average way, so in my scale, that was a 6. But somehow, other jurors give a high 8, so let's have, maybe you should comment on your 8.
Okay, I agree with most of the points you raised. The only missing point I already told what was missing, but the rest I completely agree with your statements.
Thank you very much. Thank you all the juror, and also thank you all the participants. This is the conclusion of the second stage, and this time, please be punctual. Okay, we're going to start at 40, like 11 minutes from now.